It's one of the gas industry's riskiest ever projects, the construction of the longest subsea pipeline in the world. Giant ships will lay 100,000 pipes linking Norway to Britain, while space-age robots trench an underwater moonscape beyond the reach of human hands. But will the finished result survive the brutal North Sea? "120 kilometers off the coast of Norway is one of the North Sea's largest underwater gas fields. 40 kilometers long and 10 kilometers wide and containing over 300 billion cubic meters of gas. It's called Ormen Lange. Ormen Lange is locked in an icy tomb 3,000 meters below the sea, so deep and so remote that it's considered beyond the reach of man and machine. But the engineers at the Norwegian energy company Norsk Hydro decide that it's too tempting to ignore, because it contains enough gas to supply 20% of the UK's needs for 40 years. The Norwegian engineers know that there's an expanding market for natural gas in Britain, because the coal traditionally used to power the economy there is no longer sustainable. Foreign gas is increasingly being used to power the turbines that create the electricity for homes and factories, and the country needs more of it. So the engineers come up with a plan. It will take 10 years and cost $10 billion US. First, they'll drill the Ormen Lange gas deposit, transport the gas 120 kilometers to one of Norway's largest processing plants at Nyhamna, and then send the processed gas down the Langeled pipeline to the UK. A total distance of 1,200 kilometers. But to build the world's longest subsea pipeline this far and this deep will mean overcoming some major obstacles. They'll need to drill nearly 2,000 meters through the seabed to tap the gas field. To do this, they'll use a rig built right on the sea floor. But the first problem is the Storegga slide. The pipeline that will bring the gas out of the field and deliver it to the plant has to scale this 300-meter underwater cliff face. And the terrain of the sea floor is too rough to lay pipe on, so they'll need to trench it. The gas itself is a dangerous mixture of debris and frozen water, capable of blowing a processing plant apart, so they'll need to adapt the system to handle this gas. The plant is big enough to turn through 70 million cubic meters each day. To handle this massive job, they amass some of the largest industrial ships in the world, each designed to tackle a specific phase of the deep sea construction. Out here in the harsh North Sea, humans are confined to the topside world. But beneath the waves, the brawn work is done by underwater remote-operated vehicles, or ROVs. These machines are so technologically advanced that they're almost the stuff of science fiction. It's a monumental challenge, but with so much gas industry money behind them, the engineers can dare to dream. But are they going too far? Can they make the dream come true? Or will the project become a nightmare? First, they search the world for a gas well platform which will work in these torturous seas. Existing designs all fall short. The weather here is too stormy and the water too deep. So they come up with an ingenious solution. If they can't bring the gas up to a rig, why not take a rig to the gas? Inside this warehouse in Tonsberg on the coast of Norway, the key to solving this engineering challenge is built. In a daring move, the engineers combine the function of a surface platform with a seabed drill guide. Called a template, it's essentially an underwater gas platform that will guide the drills through to the gas field and control the well flow. Conventional gas platforms are surface structures manned by an army of workers. but in this case, the platform will be dropped onto the seabed where it's clear of the wild North Sea weather. A drill ship will then dock to it and from above guide the drills through to the gas field. When the drilling is done and the gas is flowing, the drill ship will depart, leaving the template to control the wells. 4 of these monsters will be mounted onto the seabed, and through them, a total of 24 wells will be able to siphon over 70 million cubic meters a day from the gas field. The template will then direct and control the gas flow to a shore-based plant. The entire unit will be operated by remote control from a manned center 120 kilometers away. Richard Bainan is a subsea engineer.
The main thing that you've got, the difficulty that you've got, is it's dark, it's the devil of a job to put it in the first place. You've got to get this equipment onto the floor. It's highly valued, highly priced piece of equipment, and then you've got to put it together with robots and you've got to make sure it doesn't leak. And apart from that, it's easy.
The stakes are huge. The engineers have to build it to withstand pressures that would crush a normal submarine, and it has to operate flawlessly for more than 40 years in a harsh saltwater environment. Once it leaves this warehouse and is lowered to the sea floor, there'll be no going back. It will be committed to the seabed forever. The 1,000-ton structure can't float on its own, so it's loaded onto a seagoing barge for transport to the drop site. With all the planning and building behind them, it's now the weather that will determine if the mission is a success or a failure. They plan the 4-day journey to the drop site to coincide with summer, the season of the calmest seas. Not that that means much out here in the North Atlantic. They rendezvous with the world's largest crane ship, the Thialf, a super crane that does heavy lifts at sea. The 2 cranes mounted on board can lift over 14,000 metric tons, about 80 747 jumbo jets. The barge and Thialf wait for a weather window before lift operations can begin. The contract to install the subsea component is worth $21 million. With so much at stake, they do a practice run back on shore. The crane and ROV operators rehearse the drop in a 3D virtual underwater world to simulate the one they'll be working in. Weather, depth and weight will all be against them. Finally, it's time for the real thing. Lines are connected, and the record-breaking sea drop begins. This is their only chance. If they miss, and the structure settles on the seabed in the wrong place, they'll have to build another one and set the project back by a year. Computer-controlled thrusters hold the crane ship over the drop site. As it drops below the surface, the underwater ROVs go into action and take over as the eyes of the operation, feeding video back to the control room. The engineers scan the rig for problems as the pressure increases. From 1,000 meters below, the ROV sends video back to the crane operator, who then adjusts the orientation. The ball bearing has to be kept as close as possible to the center of the bullseye. He keeps the drop going even when it's just meters away from the sea floor. There's no stopping it now. The template is down, and so heavy that the legs on the base sink 8 meters into the seabed. But the engineers won't know if they've hit the right spot until they check the coordinates. Readings show it's within 40 centimeters of their target, close enough to be considered a perfect drop, and it was accomplished from 1,000 meters above on a rolling sea. Now that the template has been successfully placed, the next step is to tap the gas field. It will take 2 years to drill the first 8 wells, and they'll need to be ready to go before the pipeline can be connected. A specialized drilling ship called the West Navigator is moved into position over the top of the gas field. The Ormen Lange gas wells will be the largest deep-water wells drilled in the world. The engineers use a powered drill head operated from the ship. Once assembled, the pipe is lowered through the bottom of the ship and down 1,000 meters to the template. From there, the drill head travels another 2,000 meters through the seabed to the gas deposit. It then snakes its way through the gas pockets. Every step of the way is monitored and recorded in a virtual database which is always expanding and is used by engineers and surveyors to plot the next drilling position. Back on land, the team can enter the cave, an amazing 3D undersea simulation. By virtually passing over the seabeds in the gas find, they can locate the most promising parts of the deposit. From the cave, Jens Grimsgaard can plot the drill's movement.
With a joystick, I can also fly in this world by just using it, this tip here, and using my movements of my hand to steer myself through this reservoir.
During the process, data collected by the drill is sent back in real time to the database. The computer then generates images which put the team right in the gas deposit. They can pinpoint spots from 10 kilometers away with astonishing accuracy.
That would be compared to that your dentist would be in the 10th floor and you would be situated in the first floor and he's going to fill out one of your tooths back there. We're getting extremely good results by doing this.
The template gets its power from the land through a 125-kilometer long control cable called an umbilical. This cable carries huge amounts of electricity, enough to power 20,000 homes. Combined in the umbilical cable are tubes carrying hydraulic fluid, fiber optics, and electrical cables. The welds on these tubes have to be as strong as the welds on the pipeline. This is the fuel and control connection to the template. Without it, the template would just be 1,000 tons of useless metal at the bottom of the North Atlantic. Because the cable is so long, it's built in a factory on the dock, and as it's made, it's fed onto a giant spool on the deck of the Scandi Neptune. Once the entire cable is spooled up, it heads out to the Ormen Lange gas field to connect the control room to the 4 underwater templates. But now the engineers have to prepare the seabed. The bottom of the ocean under the North Sea is a treacherous place, and the team building the world's longest underwater pipeline is about to face a mountain of trouble. 8,000 years ago, 2 pieces of Norway, each about 300 square kilometers, slid into the sea, causing a mega tsunami. The landslide, known in Norwegian as the Storegga, created a huge shelf in the ocean's topography. The Ormen Lange gas field is on the edge of the Storegga, locked inside the huge depression left behind by the slide. This underwater disaster created a mountainous seabed with peaks that rise between 25 and 55 meters. The biggest concern for Hydro is how to get the pipeline up the Storegga slide face, a whopping 300 meters. Underwater surveys reveal a rugged and fractured seabed, but any unstable sediment has long ago disappeared. The rock is more than stable enough, and it would take a new ice age to dismantle it again. But the study has made the engineers more aware of the seabed and the pathway they'll need to clear for the pipeline that will connect the underwater gas rig to the land. First, they need to build a 3D model of the sea floor and find the easiest route. To do this, they create a virtual reality program. The fisheries in the North Sea comprise a huge industry, and Hydro has to make sure the pipeline won't damage the reefs where fish feed and fishing boats work. But the concern isn't just the environmental impact at sea, but also on shore, where one of the largest gas plants in Norway is being built. The land connection they've chosen is the small island of Gossen and the tiny community of Nyhamna. The destiny of this quiet community will be forever altered now that it's been designated the landing area and processing plant for the Ormen Lange gas project. What was once a remote corner of Norway will be transformed into a bustling industrial center. Here, raw gas from the Ormen Lange gas field will be converted into usable fuel. But to do this, more than 2 million cubic meters of rock must be carved from the island and over 30,000 tons of steel brought in. Almost overnight, this small village becomes the busiest construction site in Norway. Over 2,200 workers are on the job site each day to keep the huge gas plant rising from the rocky coastline. There's a canteen to feed 1,000 people in a sitting. Each night, the workers retire to the hotel, which will provide 1 million guest nights over the course of the project. But once the processing plant is up and running, it will be removed. Three-dimensional models of the plant have already been built, and the engineers can virtually walk through it before and during construction. Every bolt and I-beam of steel is pre-visualized. Because of the volatile gas, the specifications have to be executed perfectly. But the plant is also built for efficiency. Raw gas will travel through the pipes and be converted into usable fuel in a mere 10 minutes, then be ready for delivery to the UK. The gas processing units are delivered to the island by ship, then cranes offload the components onto massive flatbed transport. This remote-controlled monster has 48 independent axles and 96 wheels. It expertly shuttles the thousands of components needed to build the plant. Here on land, the workers have a hands-on relationship with the job site. But offshore, workers have downed wrenches in favor of joysticks. The underwater work is done using ROVs, everything from pipelaying to heavy lifting. So a lot of different ROVs are required, and a lot of people to operate them. This warehouse contains a simulation tank, built so that offshore personnel can train on ROVs. Here they simulate projects that will take place offshore. It takes special tactile skills to maneuver a crane arm from 1,000 meters away. Multiple cameras allow the operators to see the action. After the intense training with the ROVs, they're sent offshore, where the stakes are high and there are no second chances. This is the Pipeline End Termination Unit, or PLET. It's a big machine with one simple task: to connect the underwater template, or gas well, to the Ormen Lange pipeline. But this is harder than it sounds. The 35-meter long, 30-meter wide, and 350-ton device is lowered 1,000 meters to the sea floor. Once there, engineers assemble its components. Called modules, these components make the crucial connection between the template and the pipeline that feeds gas to Nyhamna. All the connections at this depth are made with remote-operated vehicles. But before any of this work can be done, the systems must be tested. Thomas Berndt is the subsea manager.
We are testing and testing and testing here, and when we leave this hall, we are 100% sure that this connection will be tight when we come offshore. There won't be any leakage. A leakage offshore at 850 meters with large volumes of gas is a disaster, which we have to avoid.
They practice lowering the modules and testing the connections, which will handle 70 million cubic meters of gas each day. They train with an exact replica of the one that's on the seafloor. It's a large investment, but it's money well spent. Surrounding the connection module is a steel cage that protects it from any stray objects that could drop off the drill ships and fishing trawlers. When the gas exits the field, the steel pipe expands. A little bit of expansion isn't a problem. But the engineers expect the Orman Lang pipeline to expand along its entire length by as much as 1 meter, enough to rip it apart. They've solved this problem by using a connector that slides back and forth on rails. This will absorb the pipe's movement and keep the gas flowing. Meanwhile, engineers are tackling the Storegga slide and trying to get the umbilical cord from the template to the control center 120 kilometers away. To do this, they have to find a way through the rough and tumble terrain left in the wake of the slide. The solution is to build an underwater excavator, agile and strong enough to handle the job. It's a daunting prospect. And the answer is a spider. The machine that inspired this one was originally built for the Swiss forest industry. Like its Swiss cousin, this spider moves on powered tracks using articulated legs. Its mission is to excavate 6 trenches at depths of up to 1,000 meters. The biggest trench will be 4 meters wide by 4 meters deep. One spider is equipped with a powerful shovel, strong enough to cast aside a 3-ton boulder. The other spider has a suction nozzle. Powerful water jets break up the sea bottom, then the nozzle sucks it up and fires the mud to the side. All the while, the spiders will have to contend with slopes of up to 35 degrees. There are sensors on all movable parts connected through an umbilical from a support vessel which floats above and monitors progress. The umbilical carries power and control cables and lets operators manipulate the 6-meter-long spider to within 10 centimeters of accuracy, from 1,000 meters above. It's an unprecedented mobilization of such complicated and agile robots. In all, these 2 champion diggers managed to excavate 3,500 cubic meters of soil and create a safe path for the gas pipeline. The Langeled, which will run 1,200 kilometers from Norway to the UK, will be the largest subsea pipeline in the world. Building it requires 1/3 of the world's combined pipeline production capacity, over 1 million tons of steel. The value of the pipeline contracts is a staggering $700 million. Langeled uses pipes over 1 meter in diameter, and each single piece of pipe has to be able to withstand the enormous pressure on the sea floor for the next 40 years. The pipes are each 12 meters long and weigh 10 tons. And another 10 tons of concrete and metal is added to give them enough weight to stay on the ocean floor. A total of 100,000 steel pipes are needed to span the distance between Norway and the UK. That includes over 1 million tons of concrete and 25,000 tons of steel reinforcing. Robert Payne is the man responsible for the integrity of the pipeline as it's being assembled.
Each joint of pipe weighs about 20 tons, about 10 tons of steel, 10 tons of concrete. It's concrete and it's got inside of it a wire mesh foundation to help it stick together. There's so much volume inside of it whenever it gets on seabed and it gets light of air, it wants to float, so the concrete keeps it situated on seabed.
Each of the 100,000 pipes is numbered as it comes out of the plant and is destined for a specific location in the line. As the team trenches on the steep Storegga slide, the rest of the route from the top of the slide to shore is being prepared. This is the Island Frontier, a state-of-the-art trenching ship that combines 2 trenching methods in one powerful machine. Engineers survey the flat areas where they think they can bury the pipe by scraping a trench through the sandy bottom. But what they discover is not a pretty picture. The sandy bottom is actually clay, and the clay has hardened like concrete. A new digger is required to cut a channel up to 7 meters wide and 5 meters deep. The margin for error is only 50 centimeters on the width and a crucial 10 centimeters on the depth. The clay cutter hybrid, the only one in the world, is lowered to the seabed. The cutting tool uses 24 water jets set at different angles to blast a trench through the clay. Suspended above is the 4-ton jet prop. The propeller draws in large volumes of the surrounding seawater, driving it at a high force towards the seabed and clearing debris from the trench. Transponders mounted on the sea floor relay a 3D picture of the operations to the control ship. And following along the entire operation is an ROV that surveys the trench and confirms that it's dug to specifications. The battle is finally won. But when they start to lay the pipeline on the seabed, the problems really begin. The seabed under the North Atlantic is a tortuous, irregular landscape, and there's over 1,000 kilometers of terrain like this along the pipeline route from Norway to England. It's so rugged that only small sections of these heavyweight pipes will actually make contact with the seabed. This is called free spanning. It's something the engineers don't want because it means the unsupported sections of pipe could sag and break under their own weight, causing an environmental catastrophe. They have to find some way of flattening out the route.
If you're not able to plane the seabed flat by moving the earth out of the way, you may have to fill in some holes with rock or other fill material.
They leveled the pipeline route by laying gravel on the sea floor. This ship loads gravel into its cargo holds and delivers it to the area that needs leveling. It can carry over 9,700 tons of gravel at a time. Once at the job site, it uses a flexible fall pipe to place the gravel onto the pipe pathway. Computers create a 3D model of the seabed and the path where the gravel needs to be placed, allowing the crew to place the gravel precisely where they need it.
At these sort of water depths, you've got a problem because you haven't got that degree of control. I mean, whatever's doing the work down there is a huge distance away from the mothership, and they've got to still present a flat, smooth profile for the pipeline then to be laid upon. The other thing that has to be worried about is that you have to do that profiling as close as possible to the time that the pipeline is going to be laid, because Mother Nature tends to move things around again after you've left. And so you come back in a couple of weeks later and you find there's been a storm or whatever, and what you've taken so much care to flatten out has all of a sudden been moved around again. So you would lose the work that you've done before.
The pipe laying itself is a monstrous job. Once the pipe has been manufactured, it's placed onto supply ships for delivery to the pipe laying barge, the LB-200. The barge is longer than 2 football fields, an enormous floating steel welding factory, which has to work with military precision. There are only 3 of these ships in the world, and Hydro is using 2 of them here.
Pipeline route has been surveyed before we ever came here. We have an ROV boat that stands by with us. It monitors the pipe as it touches seabed, and it's a predetermined route that we follow.
The barge has been used in the Gulf of Mexico, in the Mediterranean, and off the coast of West Africa. But this is its biggest and most historic assignment. Once the pipe laying process starts, it can't be stopped, not even for weather or accidents. The pipeline is built as a continuous tube that's dropped from the ship to the seabed. If the ship halts for too long, the strain on the pipe could snap it. The barge moves along at 4 kilometers a day and needs a constant supply of pipe sections, which must be delivered in the order in which they're to be connected and laid down. 100,000 pieces of pipe are laid down end to end in a predetermined pattern.
They get moved by crane 3 or 4 times and go through about 15 or 20 welding stations and coating stations.
pipe sections are delivered to the assembly floor, deep inside the LB200. Here, the welders are divided into teams. Their job is to create sections of pipe called double joints, each 24 meters long. There's a lot at stake. The pipes have to be put together so there's no chance of leakage, and the assembly line has to keep up a steady pace. The entire operation is monitored by engineers who have video cameras that watch the process both inside and outside the pipe.
It's incredible technology, but the fundamentals are very simple. The fundamental thoughts that go behind it, because it has to be so rugged and it has to work every time, first time, the actual basic engineering is still fairly simple.
The next stage of the assembly line is to join this short section of pipe to the main pipeline. It's fed out of the back end of the ship and onto the sea floor. It's a complex process that requires a lot of fine-tuning. This is no ordinary welding operation. The process involves a special welding machine with 8 heads per station. Passing through each of the welding stations in 7 minutes, the pipe is then checked by an ultrasound machine. If a flaw is detected, it has to be repaired immediately before moving on to the next station. The process can't be stopped, and the connection has to be perfect, because this is the stage that welds them together forever. The assembly line is manned by industrial workers from over 30 countries. Shifts work around the clock to keep the assembly moving 24 hours a day. Each day, the teams have to assemble 3 to 4 kilometers of pipeline and drop it to the sea floor. After the welding stations have linked the pipe, the final step of the operation is to seal the exposed metal. It's covered in a protective heat-shrunk plastic. Without this, the steel pipe would corrode in the seawater. Then it's time for the most critical step of the operation, offloading the pipe to the sea floor. The section where the pipes are joined is covered in foam to protect the welded joint during the drop. The decks are cleared, and the pipe is ready to be committed to the sea floor. A rubber tensioner grips the pipeline and holds it in place as it slides off the barge. As the pipe enters the ocean, it begins to sag, and pressure is put on the entire pipeline, which is free hanging beneath the ship. Without exactly the right tension, the pipe could snap.
The pipe comes off the back of the barge in what's called a lazy S configuration. So it comes off the back of the barge and trails down to the seabed some distance behind. That S of unsupported pipe has to be kept from just buckling under its own weight. So to keep it under control, you've got to keep that under a huge tension to stop it from just collapsing under its own weight.
As the pipe is lowered, the barge moves forward exactly 24 meters. With this well-oiled operation, the LB200 is able to lay over 100 kilometers of pipeline a month, as long as the pathway is clear. But clearing that pathway is a complicated process. In these particular sections of the pipeline route, a 2-meter deep trench is required. So engineers bring in the massive Saipem plow. This is the PL2. It's being used for trenching in shallower waters. It drops onto the seabed over the 1-meter diameter pipe, where its strong clamps pick it up. Then, as the surface ship pulls it forward, the plow cuts a trench 5 meters wide and 2 meters deep. To fill the trench, the BPL-2 follows behind with backfill to cover the pipe with a protective coating of sand. Early in the design phase, engineers decided to bring the gas from the Ormen Lange field to the processing plant at Nyhamna and then build another 1,200-kilometer pipeline to Britain. At the 600-kilometer mark, the line is broken and connected to the Sleipner riser platform. The Sleipner platform works as a hub, monitoring the 70 million cubic meters of gas flowing into the UK every day. But tying the pipeline to the platform creates a whole new set of engineering headaches. The underwater robots line up the pipeline and the connecting pipes coming from the platform. A massive underwater crane moves them into position. But when they're matched up, there's no technology that can replace human beings in making the final connection. So the welders also have to become divers.
You ready to come down? Your hose good? Okay, he's ready to come down.
Thank you.
The divers move around the worksite in pressurized modules, welding on the sea floor.
Do one lift on it and see if we can rotate it into its proper orientation with you guys. Oh. Hey, you're clear of that, Dearman?
New edges have to be cut and beveled at each pipe end before the welding hub is lowered onto the joint to connect the two sections. The welding habitat is dropped to the ocean floor, then maneuvered in place perfectly over the 1-meter diameter pipe. It clamps the pipe and then closes itself off. The habitat is pumped full of air, forcing the water out. On the surface, the dive supervisor uses cameras to keep a close eye on the underwater team and watch for any danger. Once it's safe, the divers move from the module to the welding habitat. Within this habitat, the diver welders make the final permanent connection. It's a tricky and dangerous procedure. The welders are confined to this small room 72 meters down, and there's no escape if something goes wrong.
Then we inch down to 6 o'clock with the weld head.
As each weld is finished, the engineer checking by monitor on the ship above is able to inspect the work. This last weld completes the connection from Easington to the Sleipner gas platform, halfway from Norway. This is the first of many underwater welds they'll need to make all the pipe connections and get the gas flowing. 600 kilometers of pipe still have to be completed, but a major goal has been achieved with this connection. A mysterious shipwreck has been found 500 meters off the coast, lying in their path, and there's no way around it. The wreck is directly in the path of the pipeline, and the engineers have no choice but to halt work. They look for alternate routes, but the underwater terrain near the coast prevents the pipeline from going around or under it. So they have to go through it. But before they do that, they decide to study the wreck and recover as many artifacts as they can. The problem is that the shipwreck lies in over 200 meters of water, well beyond the reach of archaeological divers. Marek Jasinski is a professor of marine archaeology. His team is called in to research the wreck 500 meters from the harbor.
I don't think they were really happy when they found out that there was a shipwreck lying in the way.
It may have stopped the pipeline in its tracks, but for archaeologists, this is a fantastic opportunity to excavate and retrieve a piece of history. But it's hard enough doing a proper archaeological excavation in shallow water. At these depths, it's considered nearly impossible. So the team takes the lead from the Ormen Lange engineers and uses ROVs to do the archaeological recovery for them. These vehicles now become new generation tools for the archaeologists. But the thrusters on the ROVs stir up sediment and obscure the wreck site. So the archaeologists devise a way to put an ROV on site and move it around without thrusters. The ROV docks to this steel frame, which covers a section of the wreck. Once attached, gears and pulleys control its movement with precision, and the archaeologists can get on with the job of unraveling the mystery of the shipwreck.
Our theory is that the ship was on its way to northern Russia, to Arkhangelsk, and that this ship was a part of the trade network between West Europe and northern Russia.
The find is amazing. They discover 18th century artifacts from Asia, the Mediterranean, and all over Europe. Once the sand is cleared, fully intact wine bottles, plates, and coins are collected by the remote-operated vehicles. Back in the lab, the finds are investigated. The archaeologists may never know the name of the ship these artifacts come from, but it's an extraordinary opportunity to look into maritime history, an opportunity that may never have arisen had the Ormen Lange pipeline not stumbled upon the wreck. Meanwhile, in Nyhamna, they now have to deal with the raw gas that comes out of the Ormen Lange field. What comes through the pipeline is not pure gas. It contains large chunks of debris called slugs. The slugs move through the pipeline with such force that when they reach the treatment plant on land, they have the potential to explode like liquid bombs.
And they will come into the plant with quite high velocity, and there's a lot of mass in it. So if those came into the plant directly, it would probably destroy the plant.
The solution is to build a slug catcher, a labyrinth of pipes and filters. This 10,000-ton monster will meet the debris and stop it in its tracks before it reaches the Nyhamna plant. Now the engineers have to contend with millions of cubic meters of condensate. Every major gas producer ends up with condensate, a valuable stew of raw materials that can be turned into other types of energy. The problem is storing it and then moving it. The solution here is to use huge underground caverns carved inside the Norwegian mountains. This enormous natural holding tank can be filled with 230,000 cubic meters of condensate. And the engineers don't have to line the rock caverns with anything. Water pressure from the surrounding area forces the toxic sludge to stay confined within the walls. Every 4 days, the caverns are pumped dry, and freighters haul away more than 24,000 cubic meters of condensate. This byproduct is a sort of liquid gold which can be turned into other types of fuel for the international marketplace. As the Nyhamna gas plant is completed, the final leg of pipe is laid out to the Ormen Lange gas field, 120 kilometers offshore. A special ship is required to work in these dangerous waters close to the Norwegian coastline. It can maneuver in tight spots using dynamic positioning, moving meter by meter from shore to the Ormen Lange gas field. Out here near the gas field, the Solitaire reaches the limit of its pipe-laying ability and can go no further. Its job comes to an end at the top of the Storegga slide. This is the most demanding part of the entire Ormen Lange project. The steep terrain left in the wake of the Storegga landslide requires a special pipe-laying ship. This is the S-7000, a former crane ship that's been modified with a 130-meter tower on its stern deck. It's now taller than a 33-story building. It's a floating factory, and one so big that it's easy to forget it's 100 kilometers offshore in the North Sea. 20,000 pipes are welded together in groups of 4. The now 48-meter-long pipe is then lifted up into the 130-meter tower and lowered onto the pipeline. Here it's welded to the pipeline, and then the pipe is carefully eased through a series of tensioners within the tower and lowered vertically straight off the ship. The entire operation takes a month to complete, making the final connection from the template to Nyhamna. With the final link made, the engineers have done what seemed impossible and built a super pipeline through some of the roughest underwater terrain on the planet. But will the super pipeline deliver? Regardless, it represents a gigantic leap in the technology of undersea engineering. The technological advances made here might well end up being used under the impenetrable Arctic gas fields. By the time this pipeline gets into full production, the huge army of divers, welders, engineers, and construction people will already have moved on to other projects, leaving behind them a super pipeline hidden deep under the North Sea.